All right, couple of things. Remind me, on Tuesday, did I talk about the rationale for the long homework assignments and things like that? Did I talk about that in here? Okay, good. Um, okay, so let's look at homework assignment here. So we saw last time we were dealing with a time complexity problem, right? So we took something. Well, first of all, we've been practicing with objects, and hopefully last class was somewhat of a breakthrough for some of you, that you kind of see the difference between constructors and methods and kind of how those things came together. As I looked at the previous assignment, there seemed to be a pretty big disconnect between those two. A pretty good percentage of the class seemed to want to just make constructors for everything. Like, you want to add some fractions together, that's another constructor. This is the constructor that adds fractions. We want to think about the difference between abilities that an object has versus the person who's going to build your house. When you are a person who's going to build the object, the constructor itself. So if you hire somebody to build your house, you're not going to then expect him to come back every day to flush your toilet, right? So that's a different task, right? that is a singular type of ability that houses have, or portions of houses have. So within the bathroom, there's the toilet object, and that object has the ability to be flushed. And that has nothing to do with Kohler or whatever company built your toilet. They're not flying into or driving down from Kohler or Sheboygan area, I guess, to perform that task as a fresh build every single time that needs to be flushed. So that's kind of your difference between your abilities of an object and the construction point of an object. And then our fields are that other piece where it's like the pieces of information that an object needs to know about itself, or the attributes of it. A toilet might have a color. It might have a gallons per flush rating, things like that. Figure we'll just finish the toilet example. But those would be examples of fields for that object. All right, so last class we had these fractions, and we decided, hey, if I have a couple of fractions that I've created and I want to add those fractions together, I might teach a fraction object how to add itself to another object. Let's go back to, I closed Eclipse because I had left my application running, and it almost killed my battery during the tech talk. It's pretty funny, actually.
Is it still running the...
Yeah, I hadn't finished yet. Hours and hours and hours later. All right, so inside of the fraction class, and this is an 8-core i9 processor in here too. Yeah, so it's a pretty beefy machine. All right, so we have our fraction class. Fractions have two fields. They're remembering a numerator and a denominator. We have two different constructors, two different ways we can build fractions. One way is we can give it a numerator and denominator, and it'll just build a fraction out of those two pieces. Another way, we can give it a string representation of a fraction, and we go through and split it on that front slash and ultimately give ourselves the numerator and the denominator. Okay, so we have two different ways of constructing a fraction object with different building materials. All right, but this was the homework for last class, where we decided all fractions should be able to add themselves to another fraction. Okay, ultimately returning a new fraction as a result. So in here, we're going to have a new denominator for our new fraction. And this guy is going to be the denominator that is owned by this particular fraction times the denominator of the fraction that was passed in. And then the new numerator will be the denominator owned by this particular fraction times the numerator of the fraction that was passed in, plus the denominator of the fraction that was passed in times the numerator of this fraction, the fraction that owns this add method. All right, then we're using a constructor of the fraction class. What does the new keyword do again? Go ahead.
It sets aside more memory just for that.
Yep, real estate agent gives us memory, right? Whenever you see the new keyword, whether we're talking about Java, C#, Objective-C, C++, you see the new keyword. Some of you are doing a couple of you are in the 350 class right now and you're doing the C++ stuff. You've seen the new keyword in there. At least I presume you're making objects or something like that. So you would see the new keyword inside of C++ as well. So this is not a Java specific thing. This is a programming thing. Modern languages that are based off of C++ use the new keyword. A couple of languages, like we looked at an example last class, I think, didn't we have before one of our constructors? I showed you the, yeah. So here is the Python version of this. You know, so the Python version of this constructor looks like this. And if we were creating an instance of this class in Python, we would say f1 is equal to fraction 1 comma 2, something like that. So that's kind of from last semester. This is us calling the constructor for fraction that takes a numerator and a denominator. But notice we don't have the new keyword there. In Python, it's kind of syntactic sugar. It takes it one step further. We've mentioned that constructors in Java never have a return type. So both of these guys look like methods, but they don't have a return type, whereas a method does have a return type. Why don't constructors have return types? Go ahead.
Because they're general operation things, they don't need inputs. They're just designed to run functions.
Constructors we have two constructors here, and both of them have inputs. One of them takes a string, one of them takes two longs in order to perform its task. But these guys never return a value. Go ahead.
Is it because basically they're used to put data into a class rather than export data from a class? So
Possibly. I'm not quite sure if what you said there encompasses it, but it might be close. So we spent like an entire class talking about this, right? What does a constructor always boil down to? We look at Java over here, and I'm creating some fractions. Here's my fraction Mike. This guy's, I'm calling my constructor. You just told me that the new keyword is our real estate agent that gives me a memory address. What do constructors always boil down to?
They initialize a new variable.
And what kind of value is that?
Memory address.
Memory address. Constructors always, always, always return a memory address. We even looked at Objective-C, an older language, where we had to define the value of self and then ultimately return the value of self. And self and this are kind of the same thing. Different languages, they use them interchangeably. So in an older language like Objective-C, we had to give self a value. And then ultimately we had to return the value of self inside the constructor. So we returned a pointer to this particular object that we just built. Java has the syntactic sugar stuff where it says, we're going to, things that would always work a certain way, we're going to take out. So you don't actually have to type it. Go ahead.
So it doesn't return a value if it's already returning a value?
We don't have to specify what kind of value it returns because it always will return the same kind of value every single time. Constructors always return a memory address to the point that not only did we not have to specify what kind of value it returns, we also were not in charge. Here, we'll just do it with the shorter one up here. We didn't have to specify what kind of value. We also were not in charge of actually returning the value. Java took care of both of those things for us. It says, look, you're going to want a memory address from this one. Okay? You don't have to tell me that, and I'll return it when we're done. I will return the value. There's like a little magical, invisible thing here that says return this. That's in there. Doesn't work right now because we don't have a return type, and that would break this thing. But I'm telling you that this is the value that will come firing out of a constructor, is the value of this. And we will capture that value on, so in this case, Mike, this variable Mike, which is of type fraction, will hold a memory address. What memory address? It's the value of this after calling this constructor. Does that make sense? So constructors, I don't care what language it is, always return a memory address. In an older language like Objective-C, we had to specify that we're returning a memory address, and we had to actually return it. In a newer language like Java, we didn't have to specify that we were returning a memory address because it's always going to be a memory address, and we didn't have to actually do the returning. Java did it for us, but we still had to use the new keyword to create new memory. In an even more recent object-oriented language, Python is actually not necessarily a newer language, but the object-oriented aspect of Python is, and we kind of can see that through the way it handles objects by passing self around. So objects in Python are kind of an add-on, like a bolt-on to the language later on. So they kind of have to hack the self keyword and say, all right, we're just going to pass this variable around because we're going to need it. So rather than it being ingrained into the language, the syntax supports self. All right. Because notice here, when I create a fraction, I'm passing it a numerator and a denominator. I'm only passing it these two things. This guy is assumed. I'm not actually passing that around, but this is how Python gets at that variable. Okay? But we see in Python, we don't actually use the new keyword. Now, what I'm telling you is in Java, except for strings, because I said strings are kind of like primitive types in Java, 100% of objects we build, I don't care if they're called randoms, I don't care if they're called fractions. Here's me creating an instance of random, we're using the new keyword. Here's me creating an instance of fraction with one of our constructors, here's the new keyword. I guess I don't use the other constructor anywhere in here, but if I did, it would have the new keyword. Every single time I create an object in Java, I will have the new keyword preceding the constructor. So that's one more thing that we technically could remove from the required syntax. Since it always returns a memory address, we shouldn't necessarily have to specify that we need a memory address. But Java didn't remove that for us. So Java still requires us to use the new keyword here when we're creating objects. If we look at an even newer language than Java, that looks like Java, like Swift. Swift has removed the new keyword from this side. So you don't even have to put the new keyword there. It's still there. This is that thing I keep calling syntactic sugar. It's just removing some extraneous parts of the actual syntax so that you don't have to type something that will always be that exact same thing. 100% of constructors are preceded by the new keyword. So if 100% of constructors are preceded by the new keyword, we can make the assumption that computers could do that work for us, and why should we type 3 characters? It's not a horrible argument, right? But at some point, our code becomes less and less readable as we keep removing things. Or if you take the Apple Swift version, you start having variables named with emojis, which is ridiculous. All right. But I personally like the new keyword being here because it is a reminder for us that we know that this guy, Mike, actually contains a memory address. And that guy points to a place in memory where the actual fraction was built. That make sense? Go ahead.
So for Swift, if you're setting a variable equal to another variable, both of the variables are emojis, it'd be like emoji equals emoji.
Yes. Yeah, smiley face equals poop emoji. Yep. Mm-hmm. Because it will resolve to the value of that variable. It's no different. Just instead of using words, we're using pictures to describe our variables. It's ridiculous, especially when you consider that, I mean, in real life, emojis are somewhat ambiguous, right? Somebody can send you an emoji and it might mean 5 or 6 different things to a person. Whereas programming, it's kind of pretty important things are not ambiguous. Go ahead.
So what exactly would poop emoji mean in that specific instance?
I guess it depends what I mean. So I've taught you from the perspective here that you should name your variables something reasonable. So like in our fraction class here, our fraction has 2 variables up here. One's called numerator, one's called denominator. So that's fairly self-explanatory that one of these variables is built for holding a numerator, a part of a fraction. The other one is built for holding a denominator, another part of a fraction. Well, in Swift, I can technically name those 2 things poop emoji and smiley face. It wouldn't make any sense. It would kind of break this lesson I'm teaching you that you should name your variables something meaningful. So 6 months later, when you go back and look at your fraction class, you realize, oh, yeah, I'm holding a numerator and a denominator, and that's part of the vocabulary of fractions. Those are known elements of a fraction. But if I name those some stupid emojis just because it was fun, I might forget what those even meant, right? So it's not to answer your question, it's not something that Swift chooses for us. It's we decided to use that emoji for our variable just because.
Okay, so in other words, it makes it vastly incompatible with other people if someone else goes through.
Yeah, unless it's like obvious. Maybe you have something, some emojis are clearer than others, right? Maybe a heart means love or something like that. But you have some emoji, especially when you get the string of emojis together that are supposed to mean something.
That's
Right?
really interesting.
And now you're reading these variables and you're trying to decode decoding a story, and that's your variable name. Yeah, so it's ridiculous. Emojis I don't have a problem with emojis in terms of texting and stuff. It's a way that people can maybe express themselves, and we already have a problem with texting. Sometimes you lose emotion in texting, so we've all taken text the wrong way or something from people. So it makes sense in that world. Doesn't make sense in the programming world. It's a poor use of that particular tool. We need variables to be unambiguous, and they need to have a discrete value that this is what it means. All right. Now, having said that, it would also be just as inappropriate for you to have this variable named X and this variable named Q. Those don't have meaning to us. They're both legal variables. I can go through my code here and change everything that used to be numerator and denominator to X and Q, and it'll still work. But when a human being looks at this, they're going to say, well, what does X mean? What kind of value? I know what kind of value it's holding along, but what does that value mean? So that's just as bad as using an emoji. Probably worse. We could probably have an emoji that at least gets close. A Q isn't close to denominator. All right, that makes some sense? All right, questions about any of that stuff? So that's all review, nothing new yet, but I want to keep putting these things in the context of that bigger picture. All right, so, but I can't emphasize enough. When you start hearing me say the same stuff in class, each class, those things that I keep repeating, probably pretty important things. All right, at this point now, when I point to that new keyword, you should immediately say that your real estate agent gives you memory addresses. That's what that guy does. Important. Okay? And it's not important necessarily from the perspective of, on a test, I'm going to say, what's the new keyword? I might ask that, but it's important for us as programmers to know, since this guy is present, right after the assignment operator, this guy's actual value will be a memory address. That actually points to where this fraction lives in memory. So Mike does not hold a fraction. He holds a memory address which points to where the actual fraction is somewhere on your computer. That makes sense? So this line right here tells us a story of how this is actually working under the hood. That's what's vitally important for programmers. We have to be able to look at code and understand how this code functions, because I promise you, you are not going to memorize an entire language. Did I talk about the rule of 10,000 last class? Okay, so, most of us in here have not put in 10,000 hours of programming yet, hence the length I want you to spend on these homework assignments. I haven't done the math, but I suspect I have. I don't know the entire Java language. I only know the things that I've worked with before. And if I work with things many, many, many times, they've just accidentally been committed to memory. But there's huge swaths of the Java language that I've never used. I never had a reason to use that tool. Just like you walk into Home Depot and there's aisles in Home Depot that have crap in them that you don't know what that does. Some stick with a spike on the end of it. What's that supposed to be used for? You could use your imagination or something, but there's plenty of things in Home Depot, even if you're handy and even if you've put in flooring or done roofing or whatever, there's all sorts of stuff inside of Home Depot that you had never had a need for, you would never buy it, whatever. But somebody needs it, right? Somebody might have some application for that type of thing. It's no different. But what do we expect? We expect to go into Home Depot and either the tool has instructions on it or Home Depot has, some sort of specialist for that aisle that you can say, hey, I'm trying to solve this problem at my house. What do I need? That type of thing that exists, right? So as human beings who are, let's say, somewhat handy, we expect to be able to walk into Home Depot and figure out how to get the tool and then use the tool that we actually need for the job we're trying to solve, provided it's in our skill set wheelhouse. So I'm probably not going to go and do any roofing because I don't know anything about roofing. So even though I can watch a YouTube video on how to do roofing, it'd make more sense for me to just pay somebody who knows what they're doing to do the roofing. Java's no different. Replace Java with any other programming language. When I go to the Java documentation, so I go to java.sun.com, and let's see, I'm going to go to the API reference. Doesn't matter which one I choose here. I'm going to do the frames one. These are all the classes that exist in the Java language. So inside here is going to be string, is going to be the character class, is going to be the random class, yada, yada, yada. Okay? As much as I've programmed, have I used every single one of those? Okay? I haven't used a fraction of those. But if I click on any one of these guys, so let's just click on namespace. Let's hope this is a class. That guy's an interface. Do we got a class version of that? Let's try. Here we got a class called naming. Okay, whatever that guy is, right? So inside of a class called naming, we're going to have a field summary. Okay, he actually doesn't have any fields. So we have methods. So here's a method called bind. You would think you could drag the, I bet you I just need to do that. All right, so he has no fields, no variables associated with him. He has no constructors. No defined constructor, so he gets the empty constructor just to support the new syntax. But he has a bunch of methods. So we have a method called bind, and this binds the specified name to a remote object, whatever that means, whatever this tool is for. I went into Home Depot, I grabbed this guy off the shelf, but everything I need to know about this guy is right here. I know he returns nothing. I know his name is bind. I know I have to provide him with a string, and I have to provide him with something called a remote. I can click on remote and say, what's that guy? That guy is something called an interface, which we will talk about. We haven't talked about yet, but so just forget about it for now. But we will learn what this means so that we can provide it with the right input. Make sense? When you go and get a weed trimmer from Home Depot, you have to know that the inputs to that guy has to be a mix of gasoline and oil. Okay, you can't just go and fill it up at the gas station and say, I'm good to go. It won't start. Or it'll start and never start again. One of those two things. All right, so we need to know what the inputs that we have. So this is a class I have never once used, but I'm telling you, just by understanding these core concepts I'm explaining in class, we know that he has a method called this, and it takes these two parameters. Go ahead.
So how do you, like if you were programming, and how would you decide that you need to go to this website and use the bind keyword versus?
Okay, so that's a good point. So I mean, at some point you're going to be saying, okay, I'm solving some weird problem. So if I scroll up here and look at what naming does, the naming class provides methods for storing and obtaining references to remote objects in a remote object registry. So at some point in your job, maybe you're solving a problem that is in terms of this type of thing. And then, you'll do a Google search or something like that, or somebody already at work says, oh yeah, here's the collection of classes we typically use to solve that problem. I mean, it must be a problem that is common enough that they decided to include it into the Java language. Maybe it's in storage area networks or something like that, where you're working with things that live on a server somewhere else, cloud type stuff. But at some point, it's no different than the Home Depot model, where you have to go in and say, hey, this is the problem I'm trying to solve. Where's the tool? Maybe that's a Google search. Maybe that's somebody else at your job who already knows about it, whatever it is. But they'll direct you to where that object is, where that tool is in the aisle. But you'll find that having the base knowledge of being able to read the documentation will give you everything you need in order to use that tool. That makes sense? Those skills transfer between the different tools. Most tools have a handle at Home Depot. Let's just use that as some sort of generic thing. I know some might not, but let's just say they all do. They all have a handle. Okay, so, if you look at every single tool, you know that, okay, that's where I'm supposed to put one of my hands. Some of them require two hands. We got two different little pad things to keep it from slipping and, all that stuff. Okay, so we have this kind of baseline understanding of how we might utilize the tool, because those tools are all built for a human being to use them. They're compatible with us. Where all these tools are built for a programmer to use them. So they're going to be compatible with our understanding of tools. Fields, constructors, methods. All right? And like I promised before, we're going to be talking about what this static keyword here means. So I can tell you right now that this means that this method belongs to the class. So I'll actually call this method using naming.bind instead of creating an instance of naming and then calling that instance like n.bind. Right? This keyword tells me that, and we'll talk about that. We haven't talked about that yet. All right, but having those base skills tells us how to use the tools, even though this is a tool I've never once used before. All right, make some sense? All right, so that is why when I keep harping on these individual things, harping on this new keyword, harping on variable names, harping on return types, these are all things that even in that short little lesson where we went and looked at the documentation, we see how important those pieces of information are. Harping on the inputs that come into the fraction. I have two different constructors, one that takes two longs and one that just takes a string. It's important for our attention to get dragged towards those things, because those are the first places we need to look when we decide how to use a tool. What do I need to provide this guy for him to work? And what is he going to give me back as a result? And somewhere in the middle, we want to make sure that it's the right tool for the job, that it's doing something in the realm. We're not going to use a lawnmower to vacuum our house. Most of us wouldn't use a lawnmower to vacuum our house.
No.
All right, so that kind of makes sense. So as a rule of thumb, if you're looking for which things are extra important versus which things are not, when you start hearing me repeat something for like the 90th time, probably something that you want to ingrain into your soul. All right? Okay, and I'm not just doing it to, in the big scheme of things, 25 years from now, I'm not going to lose sleep if you don't know that your variable doesn't have a memory address in it. Right? This is for you. This is for you to become a professional programmer is the idea there. Okay. So that kind of reviews everything that we've done in the last couple of classes. These are really, really, really important concepts. So if some of these things are still blurry for you, go back and rewatch the first half hour of today's lecture over and over again until this stuff really makes sense. Because sometimes I know I'm going to go fast, or it's going to, you got so many things being thrown at you during class, but that's the advantage of having the recordings. And I had one of my students tell me the other day that he's been having trouble sleeping. And I said, I've been told that my recordings are an excellent way to go to sleep. So you just kind of put it on, get in bed, and 5 minutes later you're out.
My insomnia solved.
Honestly, it's a bit more exciting.
No, I feel like, okay, now I solved it.
Well, maybe in the big scheme of things, my lectures are more, exciting than some other lectures might be, but I'm not sure if at 4 a.m. when you haven't slept in 2 days, it's going to really, it's not going to do the trick. At that point, you probably should sleep, or you might want to start chugging the Monster or something like that. Don't just throw a Littman lecture on and hope for the best. All right. So let's talk about the homework for today. We saw last time, we wrote this add function, and that guy made more sense. That was our big focus last time, is kind of that differentiating factor between constructors and methods. Okay, so do we feel at least a little bit better about that? Now with practice, we're going to become even more solidified there towards that 10,000 hours. Okay, and then we wrote this reduce function. And this guy made pretty good sense when we wrote it. We said, okay, well, I'm going to figure out which is the smaller of my two values, my numerator or my denominator, because that's the biggest value that might divide both of them, right? Then I'm going to go through and I'm going to check from the largest possible value all the way down to 1, because I know 1 will evenly divide two numbers, right? I can pick any two positive numbers and 1 will evenly divide it. That's one of the nice properties of the number 1. Okay, so 1 will evenly divide it, so I know that's my stopping case. I will get an answer here eventually. Okay, even with the thing we wrote last time, maybe 4, 5, 6 days, whatever it is, depending on the size of the fraction, you'll get an answer. Okay, keep your laptop plugged in is the punchline. This laptop typically gets somewhere in the ballpark of, let's call it 5, 6 hours of battery life in practical use. When I'm using it, it was like 20 minutes during that because it was just grinding math the whole time. All right, so we kept testing the biggest possible number that it could be. What did we say? If the numerator is evenly divisible by that and the denominator is evenly divisible by that, both of those things are true, we have found a number that evenly divides both the numerator and the denominator. And since I started at the maximum possible value that could have been, I now know I found the greatest common divisor of the numerator and the denominator. All right, so once I found it, what did I do? Well, I divided both of those things by that number, and then I returned. What does the return keyword do? Kills the function. Important. It kills the function. Notice that this function here doesn't return anything. Return can optionally be used to return a value. So like in our add function here, we advertise add will return a fraction. And we use the return keyword at the end in conjunction with the value we wanted him to spit out. But return makes a function end. And then optionally you can spit a value out. But don't try to spit a value out when you've advertised to Java that you don't intend to return a value. It will scream at you. If I try to return a string LOL or anything there, it's going to yell at me. I hover over this guy and it says void methods cannot return a value. But a common beginning programmer mistake is you might be inclined to take the return statement out. The thing is to take the value out, because void methods are allowed to end. That's what return actually does. It kills the method. Make sense? All right, so as soon as I found my greatest common divisor, I did the division and I killed my method. I'm done searching. I found my answer. Otherwise, if I didn't find the answer yet, I subtracted 1 from smallest. It's now 1 smaller, and I'll try the next guy. All right, now we could have made this a little bit more efficient by going in and doing some math tricks with like the square root of the smaller number and things like that. But we still would have been searching through a lot of values. All right, and last time we kind of purposely constructed really big numerators and denominators to really drive this point home that, hey, some programs don't just run in a quarter of a second. Some take time. And if you didn't expect it to take time, chances are you either have an infinite loop or you bumped into a time complexity problem and you need to rethink the math. And this kind of goes back to something I would have said last semester probably, and I probably said it this semester as well, but generally speaking, an inefficient correct answer is better than an efficient incorrect answer. All right? Well, that's true every day of the week. You'd rather have a working solution that's slow than a non-working solution that, if it did work, would be fast. Typically, we could even say that an inefficient correct solution is basically just as good as an efficient correct solution. Typically, we could say that. They both work. One is faster than the other, but we can say that they're just as good as each other most of the time. And if one of those you understand a lot better than the other one, use that one. Because we get to leverage the speed of our computers. We don't care that we're using a little extra memory or we're using a little extra CPU time. We don't care about those things most of the time. Does that make sense? That's a kind of an important lesson there too. Don't write code that you don't necessarily understand with the effort of having one less line of code or having it run in slightly fewer CPU cycles or something like that. Write code you understand first. Then if there's a necessity to optimize it, then you can go back through and do that. Maybe your job says, well, this all has to fit inside of 32K. Then you have some constraints. Maybe your job says this has to run in less than 1/10 of a second. Now you have some constraints. But generally speaking, solve it accurately first in a way that you understand. Don't try to get fancy with it. Go ahead.
So I've been thinking about this for a little bit,
Mhm.
and basically I understand that why we're going through this. It's a good problem to understand.
Mm-hmm.
Doesn't the fact that Java doesn't let you use fractions properly make it a worse program?
Well, Java does let us use fractions. Well, Java doesn't have fractions built into it. We're building our own. So Java lets us use fractions properly. We're doing correct reduction here. This is accurate. This is an accurate reduce method. This isn't something Java gave us. This is something we wrote. We use Java syntax to express a accurate solution to reducing the numerator and the denominator. And it does allow us to have a better solution, but it also allows us to have this solution that makes maybe more sense to most of us. Because if you looked at the Euclidean algorithm I gave you, it's a mathy thing. It's not that long, but chances are most of us wouldn't have looked at it and said, oh, I really understand the math behind why this works. It just works. That's why they named it after a guy. Okay, they named it after Euclid. Said, smart math guy came up with this thing. Works super fast too. Thumbs up. Okay.
Very nice.
It's the ultimate tool. It's the really expensive tool in the back of Home Depot that says, hey, you want to paint a wall? Well, you can spend 17 hours painting it, or you can use this awesome machine that will paint the entire wall in 4 seconds. And everything else around it.
The robot.
All right. So does that make some sense? It's not that Java gave us fractions. It's that Java gave us a syntax for us to express a solution to a problem. And the reason why fractions are a good solution to this is it's something we should all understand. We've all had fractions in a math class at some point, probably in like 3rd or 4th grade or something like that. Okay, maybe we had to refresh our memory on it because it's been so long, but it's not hard math, right? And so we can conceive of the problem, but it's also a problem that happens to run into this time complexity problem. So we can prove to ourselves that, oh, you know what? Sometimes when we try to follow that approach of let's solve a problem in a way that makes a lot of sense to us, sometimes we will have an accurate solution that actually is not an appropriate solution because we don't have a week to wait for the reduced fraction. That makes sense? And that's why we have some of these algorithms. We can invent our own algorithm that might do something really cool and they'll name it after us. Or we can use some of these pre-existing algorithms that exist for doing some of these things. We're going to be looking at an algorithm probably next semester, but it might be at the end of this semester, called the shunting yard algorithm, which sounds a little intimidating, right? Just because it has a weird name. But it's an algorithm for how do you remember that problem we solved in 200 where you had like process expression like 123 plus 5 divided by 2?
Yeah.
And I specifically said you can go through that guy. You only have to make it work left to right instead of order of operations, because order of operations makes that problem way harder. Shunting yard solves that version of the problem. It's an algorithm using stacks and queues for solving the problem of orders of operation. And because it's a hard problem otherwise. That makes sense? And we probably could, plop together our own little version of that algorithm where it's like, all right, I'm just going to store all the symbols, I'm going to store all the numbers, and I'm just going to ask a zillion questions. and use the right operator in the right order, maybe.
And credit works.
Yeah, or this other person came up with a relatively concise, pretty easy to follow once you get past the intimidation factor version of the algorithm that says, this is how you can make it work. And it's a fairly easy thing. It's a good way to practice stacks and queues. All right, that makes sense? Go ahead.
So we can have like fraction as an output type, right?
Mhm.
But we can't put like any word in for output type. Like fraction is in some Java output type library along with string and int, right?
No, it's in this one right here. We invented it.
Oh, okay.
So our output type can literally be anything that is either one of the primitive types, one of the types that's already built into the Java language, like you just mentioned, like strings, like characters, like what was the thing we just looked at? Naming. Yeah, so our output type can be naming, or it can be anything that we invent.
So any class.
Any class. Any class that we make. Could also be interfaces. We haven't talked about those yet. But for right now, any class that we make is now a legal return type. Make sense? All right. So we know that this reduce function takes too long. It makes sense. The code is easy enough to follow once you kind of take a step-by-step approach to it. Feels pretty easy mathy-wise. Just takes too long for big fractions. It worked on small fractions just fine, right? Didn't we reduce 6/8? Pretty quick, no problem. Because we only had to count from 6 down to 1.
Well, then when you get
Right?
0.2
Oh,
billion.
Yeah, not the quintillion number down to whatever. That's a couple more, a couple more significant digits, right? So we go and look at greatest common divisor. I gave you a link to the one that has like the algorithm in it. All right, so just put this in here. Okay, so we run into Home Depot. We find this tool. I'm just going to copy it for a second here. I'll go back in here and I'm just going to make a quick little, no, that didn't look as nice as I expected it to, but that's okay. It's short enough that it doesn't actually matter. All right, so I'm going to translate this pseudocode into Java equivalent. All right, so for reduce Euclidean, I'm going to give myself 2 values here, and we're doing this based on longs, right? So I'm going to have a long A is equal to this dot numerator. A long B is equal to this dot denominator. So those are my A's and B's in terms of this function here, right? Okay. While B is not equal to 0, what am I going to do? I have a new variable called t. So I'm going to say long t. Just give myself a variable. I'm going to say t is equal to the current value of b. Then I'm going to say b is equal to a mod b. And then I'll say a is equal to t. That's what these lines say, right? Set t equal to b, change b to be a mod b, then update a to be the old value of b. In the end, we'll say this dot numerator is equal to this dot numerator. And I think in the end, so return a is our actual greatest common divisor. So that's going to be divided by a. This dot denominator is equal to this dot denominator divided by a. And that's our final answer. This is the Java version of this algorithm. So I'll put a little comment here. A is our greatest common divisor of A and B now. So let's say A is now our greatest common divisor of numerator and denominator. Make sense? So now I can come out here to driver, and down here where I have commented out reduce because it was problematic, I will go in here and instead of saying reduce like this, I'll say reduce Euclidean, and I'll run this again, and it run, well, actually this is a bad starting fraction because it went to the negative, so let me just run it again for our randoms.
It takes about a century. Wow, you're getting really bad luck.
I am getting bad luck.
You're rolling the dice and you're getting.
There we go. All right.
Don't
Big numerator, big denominator, basically reduced almost instantaneously. Right?
Right.
That's GCD. I'm not here to teach you the math underneath GCD. You can go research the Euclidean algorithm, all that stuff. I couldn't even tell you what the math behind it is. I feel like I could probably understand the math behind it, and at some point I probably had a math class. You talk about that kind of thing? Yeah, at some point I had a math class about that, but that was a couple of minutes ago. So you guys are very lucky you don't have to take as much math as other CS schools. Well, I would say it's unfortunate you don't have to take as much math. Personally, I had classes you wouldn't even. I had a class called combinatorics.
What?
Looks up from one of my bosses.
Yeah, Gesundheit, right?
My combinatorics.
Because I went to University of Illinois and they had, they're a fairly top tier engineering school. And so there's basically their computer science math requirement made it so that you would be stupid not to do a math minor. You needed like one extra class. They basically said, take all the classes that you've heard of. And then take the one that you've never heard of. That's a made up word. They literally randomly generated the name of the class every single semester. And it was just as appropriate as the real name of the class. I had a crazy guy for that class too. His name was Samson Adeliki. Yeah, and he was this guy. I think he was from somewhere in Africa, but he had a British accent, and he would bring his own chalk to class. We had chalkboards then, so he brought his own chalk to class. He colored chalk, and he always. And I think Pastor Smith does something a little bit less crazy, but something similar. I think he invents these students, and then those students kind of go through his lectures for like a 4-year period of time, right? I've heard him reference them at chapel. But this guy, Samson, he would be up on the board. He'd draw this, stick figure and said, "This is Mary. Mary was a very diligent student, very diligent. She'd work on a problem. If she get it wrong, she'd rub it off, try again." This guy was full-blown awesome. And there was like 5 of us in that class. He didn't have a clue what he was talking about. But it was really interesting. It's actually kind of math for computer science people is what I would say combinatorics is. It's like a statistics on steroids-y type stuff. So interesting class. But
Imagine Linder
Yeah.
teaching like that.
once upon a time, there was some math stuff stuck in here. That's all gone. So now I stick with fractions.
Yeah.
That's what we do. Okay, but this is a Java implementation of the Euclidean algorithm. So what does this code right here do? It sets A and B out of convenience because those are the variable names used by the algorithm I had. A to my numerator, B to my denominator. Didn't matter which of these two I used because I'm looking for the greatest common divisor of those two values. Okay, that's what this guy solves, the greatest common divisor of A and B. And I need a temporary variable. I go through, I whittle B down until it's finally a 0. Temporary store the current value of B, update B, set A to the old value of B. Do that over and over and over again. In the end, you'll be left with A, which is the number is the largest number that will divide both the original A and the original B, our numerator and our denominator. So I divided my numerator and denominator by that value. So now we went from a version of reduce that took forever to a version of reduce that took a fraction of a second. Make sense?
Yeah.
All right. So now, let's see. Let's do class methods versus instance methods. We've waited long enough. So we have two different kinds of methods. Static versus non-static. I'm going to call these guys members. We've already talked about the members of a object, the members of a class are fields, constructors, and methods. All right? Now, constructors are kind of weird. So, they're different. They look a lot like methods, but we spent a good amount of time today already talking about that. Always have the same name as the class, never have a return type, never return a value because they always return a memory address. That's what constructors are. So I'm going to just put in here, except constructors. So we could say that, or we could say static versus non-static fields and methods. Both of those mean the same thing. Fields being our variables, methods being our abilities that an object knows how to do. So we're going to start off by saying static. This guy means it is owned by the class and is therefore referenced by using the class name itself. Non-static means it is owned by an instance of the class and is therefore referenced by using an instance of the class. All right, so we're going to have this becomes one of our mantras here. So static members are defined using the static keyword. They are called using the name of the class in which the field, well, let's say in which the static member was defined. Because we have two different sides to programming, right? We have defined a class called fraction. That's like a blueprint that teaches us how to build fractions. And then we use that blueprint, we use that class to actually build some fractions. So we go back to the code here. This is where I am defining a fraction inside of this. But at this point, I am not obligated to ever use the fraction. I went to Home Depot, I bought a fraction, brought it home, never touched it. Plenty of tools we've done that with before, right?
Yes.
Okay? So this is an untapped resource. It is a blueprint for accomplishing something. I am in no way obligated to ever use it. Over here in Driver, I have decided, now, right now, Driver is where I have used it, but it's not the only place I can use it. If we look back at fraction and we look at our add method uses the fraction class as well, does it not? I create a new fraction inside of the add method. Does that make sense? So I'm not stuck with only using blueprints inside of Driver. I can use blueprints wherever I have access to that blueprint. And for our world right now, we're going to say it's anywhere inside of our project. Let's leave it at that. It's a package thing, but just anywhere in our project, we have access to our blueprints. All right, so here's an example of me using that fraction class to create a fraction. Here's me defining the fraction class. Make sense? All right, so let's go back to the slides here and then we'll look at an example of it. So if I'm looking at a static member, a static field, or a static method, I will define it using the static keyword. And we've used that in front of methods already when we had them all in Driver. And I'll kind of explain that soon. Okay? But when we define a static field or we define a static method, what we do is we put the keyword static before the definition of the field. We put the keyword static before the definition of the method. Now, this is different than the question of why would I make something static or why would I make something non-static. For right now, we're just assuming that we might want to. We might want a static member or we might want a non-static member. How do I define those guys differently? If it's a static member, we put the static keyword there. If it's a non-static member, these guys are defined without using the static keyword. Restrain yourself from typing it. Okay? So if you happen to be defining a static member, if you happen to be defining a static member, write the keyword static. If you happen to be defining a non-static member, don't write the keyword static. That's when you're looking at the definition. Make sense? When you are calling a static member, you call this guy using the actual name of the class in which the static member was defined, not an instance of the class. You'll use the class name itself. So if I had a static member inside of the fraction class, I would say fraction dot whatever, as opposed to non-static members are called using an instance of the class in which the non-static member was defined. That make sense? Now, we've already been writing non-static stuff. The beginning of the semester, we were writing static stuff because we just said, well, we're going to have this driver class and we're going to want to have some methods in here. Just put static in front of them. Trust me. Right? Didn't know why we were doing it. We just happened to put static in front of those methods because those guys had to be defined as the static keyword because of the way we were calling them. And I'll explain that here in a minute. More recently, we've been writing methods. Well, here's some fields. I don't have static in front of those, right? Which means that they are owned by instances of the class. Therefore, I would reference these guys using an instance of the fraction class. I could say Mike.numerator or Mike dot oh, because I didn't finish that guy here. Mike.denominator. I use an instance of the fraction class. So this is a variable of type fraction. That is an instance of that class. Mike, technically, if we're really unpacking this, Mike holds a memory address which points to an instance of the fraction class that was built by a constructor somewhere up in memory. Noah holds a memory address which points to a place in memory where a different fraction object, another instance of fraction, was built by a constructor for the fraction class. Okay? That's an instance, that's an instance. The variables themselves hold pointers to those instances. As long as you understand that under the hood, it's not unfair to do a shortcut and say Mike is an instance of the fraction class, because that's what he will ultimately resolve to. Mike's direct value is a memory address, but he will resolve to the fraction that lives at that memory address. So I can say Mike is an instance of fraction. I can say Noah is an instance of fraction. I can say test is an instance of fraction. Make sense? And instances of fraction have access to the instance members, the non-static members of the fraction class. Mike.numerator, Mike.denominator. These guys are non-static. How do you know those are non-static? That's where I'm defining those fields. How do you know they're non-static? They don't have static in front of them. Whoever wrote that stuff held themselves back from typing those characters, right? We don't see the static keyword there, therefore they are non-static members. Therefore, we access them through through an instance of the fraction class in this case, through an instance of the class in which the members were defined. That's this language here. Through an instance of the class in which the non-static member was defined. So these two guys are non-static members. They are defined inside of a class called fraction. So we access them using an instance of the fraction class. Mike.numerator, Mike.denominator. Make sense? I could also say Noah.numerator, Noah.denominator, test.numerator, test.denominator. I can say Mike, let's go and look at the add method here. So here's the definition of my add method. Is that a class method or an instance method? Is it a static method or a non-static method? So often I'll call static methods, I'll call them class methods. And I'll call non-static methods instance methods. Because non-static methods means they're owned by the class. Static methods are owned by the class. Let me put this on the slide. Static methods are owned by the class. So we'll say sometimes called class methods or class members, class field. Non-static methods are owned by an instance of the class. So we might call these guys sometimes called instance methods. I'll put fields in here too. All right, that makes some sense. So when I say static, I'm also talking about, if I say it's the static method, it's also a class method owned by the class. So class method is kind of a shortcut for static method. Non-static methods or fields would be instance methods or fields. These are synonyms for each other. Okay, questions about that? All right, so here is my definition of a method in the fraction class. Is this guy a class method or an instance method? How do you know it's an instance method? No static. He is an instance method because he does not have static. So the way I've defined this is without using the static keyword, therefore he is a non-static method or an instance method. How do I call instance methods or non-static methods? If it's non-static, these guys are called using an instance of the class in which they were defined.
So that would be like, is that like Mike or like Noah?
I need an instance of the class in which this guy was defined. What class was this guy defined inside of? A class called fraction. I need instances of fraction. I have 3 of them right here. I have Mike, I have Noah, I have Test. And in fact, in this example right here, Mike calls his add method and passes Noah in as a parameter. I could have just as easily said, Noah, call your add method and pass Mike in as a parameter. That make sense? I'm calling 2 different versions of the add method. This version knows about Noah. The other version knew about Mike. So inside of this version of add, this keyword is a pointer to the same place that Mike points to. If I change this to Noah, inside of this version of the add method, this keyword is the pointer to the same place Noah points to. Make sense? So because add is an instance method, I call it using an instance of the class that the method was defined in. Make sense? All right. Super, super important stuff. Being able to identify what kind of field or what kind of method you're looking at tells you exactly the correct way to call it. All right. I already put up the reading assignment. So for Tuesday, we are catching up on some reading. I encourage 2 things. I gave you reading from chapter 7. So we're officially moving towards unit testing, and we're going to be dealing with array lists here pretty soon and some other things. If you find yourself struggling with some of these things, I encourage you to go through the interactive exercises between 2 and 6. Just start going through them. You don't have to do it for Tuesday. You don't have to turn anything in. Those are reviews from what we did last semester. But it's reviews in Java and will give you some more practice. So if some of these things feel disconnected to you, that will give you extra practice to work on them. Okay, so officially the assignment I think is 7.1 through 7.8 or something like that in chapter 7 of the book, Zybook. But then you have, I'm encouraging you, if you feel like you're struggling, to go through chapters 2 through 6 at your own pace to start getting those skills up. Sound good? Questions, comments, concerns, bribes?
I think it's the first time you said that this semester.
No, it's not.
No, that cannot be the first time I said that.
swear.
What?
No.
He said that so
You think that's the first time I said that?
No, it's not.
In this class? Really?
It's the first
Interesting.
time you said that.
All right, I'll see everybody on Tuesday.